So I hope my screen is visible to everyone, right? Is the screen, my screen
Yes.
is visible? Yeah, my voice is audible to everyone?
Yeah.
Yeah. So today in this session, for the continuation of this CMOS VLSI design, so we need to go one more step that will discuss about the technology behind CMOS scaling. Now it is very important that in the conventional technology which we used in our day-to-day life, especially in the R&D or in the industry also, when we do for any fabricate any devices for CMOS, especially for CMOS devices, the one important thing is that scaling. Why it is required scaling? Because when you do scaling, then we can able to make more devices in a tiny spaces. That means the effective density of the devices in a small space we can able to make more effectively. That means if we have a few in a few nanometer space, if we can able to accompany or if we can able to incorporate let's say thousands billions of CMOS devices, then that will be very useful for us. So, but for that, the scaling is very important because in CMOS technology, the scaling plays a very vital important role. Now, the thing is that, as you know, from the conventional technology, we have our MOS devices. So we have a source, drain, and gate inductor, right? And the conducting channel length, which is there between the source and drain, that we call it effective channel length. Okay, so this is our source, so this is our drain, and this is our gate, right? And this is our the channel that we call effective channel between source to drain. Now, it is very important that whenever we do any scaling, this channel length plays very important role. Okay. Uh, as you know, this device, this MOSFET device can be used as a switch, right? Because this gate potential plays a very important role. Okay. So, as depending upon the potential which we are applying to the gate, so it can be made the current conduction from the source to drain can be takes place. So it can be act as switch because depending upon the potential that we are applying to the gate. Okay. So it can be a on switch or it can be off switch. Off switch means there will be no current. There will be no current flow, and that means at that time our switch is off. But whenever the current is on, that means when we say that means the current conduction takes place between source to drain. Okay, and in that cases, our this switch is considered to be off. Okay. Normally, if you can think of, it's we call it the ratio of on current to the off current. That means I on divided by I off. Okay. Ideally, this I on, so off current means the off current means it's considered to be zero, right? Considered to be zero. So let's say we have some numerical values of ion current. Let's say ion current is, let's say, in a milliampere. And ideally ion current has to be what? It has to be zero, right? It has to be zero. So what is the value of ion by ion? Can anybody tell me? What is the value of ion by ion? Can anybody tell me? Can anybody tell me? If ion value, let's say 0.5 milliampere, and I of is equal to 0, ideal condition I'm telling. So what is the ratio of I on divided by I of? What should be the ideal value? Can anybody tell me? Can anybody tell me what is the value of I on by I of? Can anybody tell me? Is my voice is audible to everyone? Is my voice is audible to everyone? Is my voice is audible to everyone? Is my voice is audible to everyone?
Yes, sir, it is visible. It is.
Yeah. Okay. So just I want to know that if the ion, let's say some numerical values. So ion, let's say some values we take into consideration of, let's say some numerical value, let's say 0.5 milliampere. Let's take an example. Okay. And I of that I of current, that means of current, is ideally has to be zero. So then the ratio of ion by ion has to be infinite. Okay, because I of is now zero. But ideally, this IF current is not considered to be zero because there is some leakage current flows. That some leakage current will flow from source to drain. So that actually, ideally, we won't get the on off current ion by IO. That ion current divided by IO current. We ideally we cannot get infinite value, but it it comes to be somewhere in the order of 10 to the power 6 or 10 to the power 7, which is a very significant value, right? Because 10 to the power 6, 10 to the 7 is high. Okay, so that actually it really happens when we have this kind of thing. But one important thing is that as you can able to shrink the devices, that means as you able to miniaturize our devices, this effective channel length is getting reduced. So that means the effective channel between the length between source to drain is coming to be very closer to each other. Okay. So in that cases, it is very essential that what device structure we need to adopt so that we can have a proper accompany of all the CMOS devices in a tiny space. Okay, so that we are going to discuss. Okay, so as you know, in the nano fabrication process, there are two cases we generally take into consideration. As I have already told in the class. So that is one is actually our bottom-up approach and another is top-down approach. Okay. So in a like in a bottom-up approach, we generally do to make the devices or make any devices where atoms are assembled together, and that means in an additive process where we can able to finally make a nano devices. Similarly, in a top-down approach, just like the example is generally we do for photolithography process or electron beam lithography process, where we can able to take out the atoms from the materials and we can able to make it. Okay, so that's the thing. Okay, if anybody has any doubt or something, you can just you can tell me. Okay, if in the meantime, okay, if you have any doubts, you can most welcome to discuss with me. So that just so with the continuation of this content which we are now discussing. So when we actually atoms are added together, that is called the self-assembly process, where we can able to assemble the atoms and we can finally arrive at making a nano devices. So that we call it bottom-up approach. But top-down approach is just the reverse or the opposite of the top-down approach. In top-down approach, we can afford to take out the atoms from the devices and finally we make a nano devices. So that is basically our top-down approach. So this is basically that is mostly is dealt with when we come across photolithography or electron lithography process. So all things, whether it is top-down approach or bottom-up approach, we are making nano devices. But thing is that the way or the approach is different. Okay, here in top-down approach, we are actually assembling the atoms together to make the atom to make the nano devices. Whereas in photolithography process, we are taking out the atoms from the material and finally we are making the nano devices. So that actually the cases. Now, whenever you find free time, just go through this article. It's a very famous article, and that actually plays a significant contribution and scaling of the devices as far as CMOS technology is concerned. So the paper is entitled on the design of ion implant ion implanted MOSFETs with very small physical dimensions. Okay, you just check. This paper was published in the year 1974. Just imagine. This paper was published in 1974 in IEEE journal, in Journal of Solid State Circuits. Okay, if you find free time, just go through this article. So it is a very nice article. So here in this research paper, this research group made some guidelines that how to make any devices if we want to make a miniaturization to the CMOS devices. Okay, so let's say we have a bulk that you can say it is a macro size dimension of devices, but we want to make it to a smaller dimensions. That means in the domain of nanometer, let's say. So, what guidelines we need to put for making the MOSFET devices? So that is very important thing. So whenever you find free time, just go through this research article. It's very important, so that you can get an idea actually how the small physical dimensions of the MOSFET devices plays a key role. And because of this research article only, the significant contribution has been made to make a small nano devices. Now we can able to arrive at about 2 nanometer, 4 nanometer technology process. Okay, in that process we can able to make the devices. Okay, so whenever you find free time, just go through this article so that you can get an idea. Okay, so there are different type of scaling we generally take into consideration. So first is actually we call it constant electric field scaling. As the name suggests, the electric field is actually constant. To make the electric field to be make it constant when the scaling has to be done. Okay, so let's say in the left hand side figure, if you can see there is a MOS device is there. So there is a MOS transistor in the left, and right hand side also a MOS transistor. So one difference you can find in this MOS transistor, which is we find at the left hand side, it is a bigger dimension, right? In terms of length, width, or you can say thickness, whatever the thing. So it is in bigger dimension. If you can see in the left hand side figure, whereas this right hand side figure is just a miniaturization of the this macro devices. That is bigger. Is the miniaturization version of this bigger dimension. Now, there are some guidelines we have to follow. Let's say if we have this bigger dimension MOS devices, and if we want to make it to a smaller dimension MOS devices, so what are the guidelines we need to take into consideration? So that actually our constant electric field scaling is all about. Okay. So if you can see here, in this MOS devices, we have a source, we have a drain, and the oxide thickness is here, and we have a gate electrode overview. Okay, and this is our, let's say if it is NMOS transistor, we have a P-type substrate. Similarly, in the miniaturized version, we have a source electrode, source drain, that is, and let's say if we take into consideration of NMOS transistor, so we have N plus is in here, N plus is in here. This is our P-type substrate, and this is our oxide layer, and over which our this gate electrode is there. But one the difference is that this device, this MOS devices, is just a miniaturization version of this macro devices, macro MOS devices. So, in constant electric field scaling is that we have to adopt some guidelines, and the guidelines is said that let's say K is a scaling factor. So let's say K is a scaling factor. So that we take into consideration such a value we have to take. It has to be greater than one. Okay, it has to be greater than one. So this has, if this is the cases, so how we can able to scale the MOS devices is like this. So there are some primary scaling factors are there. So what are the primary scaling factor? That means these aspect parameter that you know, channel length L, channel width W. This is T ox, this is the oxide thickness. Xj is the junction, you know, the junction thickness. So all linear dimension, whatever we have, so that we have to make it to 1 divided by k. Okay, so let's say we have this bigger dimension small device, this most devices. Let's say its channel length is L. Okay, let's say consider this MOS devices as channel length L. So what if we want to make it a smaller devices? So what we need to do? Let's say this private scaling factor is somewhere greater than one. So let's consider it as a k value. Let's say, for example, 1.5. Let's say k is equal to 1.5, which is greater than 1. So what the scaling theory tells that, so if we want to make a miniaturized version of this MOS devices, then this channel length has to be L divided by K. Okay. Similarly, if W is the channel width, then it's the new dimension will be in this for the smaller miniaturization version of the devices will be W by K. That means channel width divided by K. Similarly, the oxide thickness T ox has to be divided by K. So T ox divided by K. Similarly, junction depth, that is the junction depth that we call it this oxide uh, thickness. Okay, this constant it has to be divided by K. Okay, so this is actually the primary scaling factor. That means here we are going to miniaturize the devices, and the miniaturization we have to make in a such way that if the linear dimension is, let's say, is offset thickness T ox, channel length is L, channel width is W, junction depth is Xj. So that has to be divided by K. What is K? This K has to be any numerical value which has to be greater than 1. So I'm taking an example. Let's say K is equal to 1.5. So it has to be, let's say, channel length, for example, L. So L divided by 1.5. So that will be the new channel length for this miniaturization version of these devices. Okay. I hope this is clear to everyone. Similarly, let's say Na and Nd, it's a doping concentration, right? What is Na? Is the acceptor concentration. What is Nd? Is the donor concentration. So where it comes from? This, like in the, if we have a substrate, P-type substrate. So the P-type semiconductor means our majority carrier is actually holes, and other magnetic carriers will be electrons. So depending upon that, the P-type substrate, if you have P-type semiconductor, so that means the acceptor impurity is there. Similarly, for N plus region, that is donor impurity, where our donor concentration is more. So in that cases, so if this is the case, doping concentration would be what? So the doping concentration has to be, it's multiplied by k. Okay, it is divided into multiplied by k here. Okay, so let's say in this here in this bigger dimension this MOS devices, let's say our acceptor concentration is Na. Okay, acceptor concentration is Na. So in the miniaturization version of these MOS devices, it has to k multiplied by Na. Right. Similarly, if Nd is the donor and donor donor atom concentration, so in that cases, in the miniaturization version of this MOS devices, it has to be multiplied by k, k times this Nd. Okay, so it will be the smaller diameter for this miniaturized version of this MOS devices. It is multiplied by k. Similarly, the supply voltage that we call it VDD. Okay, for the supply voltage VDD, it is divided by K. So for this smaller devices, for this miniaturization version of these devices, our supply voltage has to be divided by K. Okay, and there are some other. So these are all primary scaling factors. And similarly, there are some other derived scaling behavior of the transistor, as it's named as a constant electric field. So in that case, during the scaling process, our electric field has to be constant. Okay, so electric field has to be constant. So in these cases, so E has to be constant. Okay, so it's quite obvious why electric field is constant. If you can see here, the voltage, whatever supply voltage, it is whatever the supply voltage in the macro scale devices, it is reduced to one by k. Okay. Similarly, the linear dimension is reduced to also one by k. And as you know, electric field is the negative of potential gradient, right? So that means electric field, let's say E is the electric field and V the voltage, and let's say L is the linear dimension. So that electric field is actually potential divided by linear dimension. But as you can see here, due to primary scaling, due to the incorporation of the primary scaling factor, the linear dimensions are reduced by k, and the supply voltage also reduced by k. So obviously our electric field has to be also, it has to be constant, okay, because supply voltage is reduced by k, and the linear dimension also reduced by k. So in this case also, the electric field has to be constant because supply voltage also reduced by k and the linear dimension also reduced by k. That is why electric field has to be constant. Similarly, the drain current, okay, the drain current has to be reduced by K. So let's say in this bigger dimension MOS devices, our drain current is, let's say, ID. Okay. So in these cases, our drain current has to be less than divided by K. Similarly, capacitance. Okay, the capacitance of these devices, if for the bigger dimension, let's say C, so it is reduced by 1 by K. Okay, 1 by K in the for smaller dimension. So it is 1 by K here. Okay. Similarly, for derived scaling behavioral circuit like the delay, that is called delay. Delay is nothing but the CV divided by I. The C the capacitance, V the voltage, and I the current. So this value is reduced by 1 by K. Similarly, power. Power is nothing but the product of voltage and current. Okay. So that actually power is reduced by 1 by K square. Okay, that is reduced by 1 by K square. So when you do any miniaturization of any MOS devices or any transistor, we want to scale it down. And if we want to apply constant electric field scaling, so these are some of the guidelines we have to follow. So, so let me recapitulate once again. So, so if all the primary scaling factors like channel length, channel width, junction depth, oxide thickness, so these are all linear dimensions, right? So this all linear dimension has to be reduced by k factor. Okay, and this k factor is such a numerical value that value is greater than 1. So this, all the linear dimension has to be reduced by k. Okay, so 1 divided by k. So one part you should always remember, when you do any miniaturization of the devices, you have to divide it by, all the linear dimension has to be divided by k. Okay, this k value is something which is greater than 1. Doping concentration, if you take into consideration, it is multiplied by K. Okay, whether it is acceptor ion concentration or donor ion concentration, it is multiplied by K. Whereas the supply voltage, okay, the supply voltage has to be is divided by K also. Okay, as you can see here, the electric field is nothing but negative of potential gradient. So that means electric field is the ratio of voltage divided by any linear dimension. So as the supply voltage is reduced by K and linear dimension is reduced by K, so this electric field also has to be constant here. Okay, so that is why that is why this is called constant electric field scaling, because the electric field is constant here. Similarly, drain current has to be reduced by K, that is 1 by K here, drain current. So capacitance has to be reduced by K, and some of the derived scaling behavior of the circuit, like delay, is nothing but the CB divided by I. So that is also reduced by K, and power, which is nothing but the product of voltage and current. So that is has to be reduced by K square. Okay. So these are the things you should remember if we want to apply for constant electric field scaling. So we need to understand that what actually the scaling we need to apply. Okay. So remember that for constant electric field scaling, we need to adopt this guidelines here. Okay, so so we have to remember. So after constant electric field scaling, we have to go another scaling that we call constant voltage scaling. Okay, constant voltage scaling. Okay, this is also another scaling. Let's say we want to miniaturize any devices. Okay, so here there is some guidelines you have to follow. But previously, we have a constant electric field scaling. So in that cases, our electric field is constant, was maintained constant. But here, our voltage has to be constant. Okay, so in that cases, if we want to do the scaling as per the this concept, then what are the guidelines you have to follow? Okay, so as per the technology, scaling is concerned, so scaling factor we have to also put the same way. So any value, the scaling factor k has to be taken into consideration, which has numerical values has to be greater than one. Okay, so one, let's greater than one means you can take 1.5 to as per your requirement of the devices, how much you scaling you want to do. If this is the cases, then this is the same thing we have to do. Here is all the primary scaling factors. That is all the linear dimension factors like channel length, channel width, this junction depth, oxide thickness. This all thing has to be reduced by k factor. Okay, this has to be reduced by k factor. So it is divided by 1 by k. So if we have a new miniaturization of the devices, then the miniaturization of the devices. So this thing we have to take into consideration. That means all the linear dimension has to be reduced by k. So what is k? With k is greater than 1. Whereas if you can see here, the doping concentration, this Na and Nd, with acceptor and concentration, donor and concentration. So this is multiplied by k square. If we compare the electric field scaling, this acceptor and donor and concentration, this doping concentration is multiplied by k, whereas in constant voltage scaling it is multiplied by k square. So this is one difference between constant electric field scaling and constant voltage scaling. The doping concentration is here is multiplied by k square, whereas in constant electric field scaling it is multiplied by k. And as you see, as you know that this it is constant voltage scaling, so we have to make the supply voltage to be constant. So that is why our supply voltage is here 1. Just like we have a constant electric field scaling, we have supply voltage. The electric field is constant. That means the electric field has to be 1. Okay, so that means there is no change in the electric field when we make a scaling. Okay, so the electric field has to be constant. Similarly, here also in constant voltage scaling, our supply voltage has to be remain the same. So there is no change in the supply voltage. But here, if we take into consideration the derived scaling behavior of the transistor, then the electric field it has to be multiplied by k factor. In constant electric field scaling, the electric field was constant, but here it is not the case. In constant voltage scaling, it is multiplied by k factor. Okay, it is multiplied by k factor. So that uh, so that is the difference between constant voltage scaling and constant electric field scaling. Drain current, as we take into consideration, is multiplied by k. Okay, so it is multiplied by k. So and the capacitance is divided by k also. Okay, so that means your electric field is multiplied by k factor and drain current is multiplied by k factor when we do any constant voltage scaling. After derived scaling behavior of the transistor, now we have to go to derived scaling behavior of the circuit. Now, if we take into consideration of the delay, okay, so if we take into consideration of the delay, so this delay is nothing but the product of capacitance multiplied with voltage divided by current. So CB divided by I is nothing but our delay parameters. So that is actually divided. It is actually reduced by k square factor. Okay, so if you have a new dimension, that is new miniaturization version of this MOS devices, we have a delay has to be reduced by k square factor. Similarly, power is nothing but the product of voltage and current, so that is also multiplied by K factor. Power delay product, that is nothing but power and time. Oh, sorry. So time delay, the product, power delay product. So this is also reduced by K factor. Circuit density. Circuit density means what is the number of transistor per unit area. So that we call it circuit density. So that if that is the cases, so that is actually also multiplied by K square. So this is very important thing. If you can see here, the circuit density is increased by K square. So this is very small thing that without affecting the the circuit behavior or something, we can able to make a more space for the transistors to be make it in a smaller devices. You can see here the circuit density is multiplied by K square. That means if we can able to miniaturize the devices, so our circuit density increases. Okay, that means the number of transistor in a smaller device is get on increasing. Okay, so that is very important thing. Now this is a another scaling that we call it generalized scaling. So this generalized scaling is just the intermediate between constant voltage scaling and constant electric field scaling. As you can see here, this electric field scaling or constant voltage scaling, we have a scaling factor, which is K is greater than 1, we have to take. Okay, it is whether it's constant electric field scaling or constant voltage scaling. So scaling factor is greater than 1. But when you take into consider generalized scaling, the K has to be greater than 1, but there is another parameter we have to take, that is called alpha. So alpha has to be greater than 1 and less than K. Okay, so let's say this greater than 1. So let's say this is 1.25. Let's say alpha is 1.25. So this 1.25 is greater than 1 and K is greater than 1 also. So we have to do like this. Okay. So we have to make it such a way that the scaling factor K is greater than 1 and alpha is greater than 1 and less than K. Okay. Now if this is the generalized scaling, the what are the things we have to take into consideration? So all the linear dimensions like our channel length, channel width, oxide thickness and junction depth. Okay, so it's all the linear dimension has to be reduced by K factor. So this thing is common whether it is constant electric field scaling or constant voltage scaling or a generalized scaling. So this factor is remain constant. It is divided by 1 by K. Okay. But here, in these cases, whether it is the acceptor ion concentration or donor ion concentration, in these cases, our new miniaturization devices, our this doping concentration is multiplied by alpha times K. Okay. So remember that in this case, general scaling, our this acceptor ion and donor ion concentration, doping concentration is multiplied by alpha K times. Similarly, if we take into consideration supply voltage, the supply voltage is multiplied by alpha times divided by K, alpha divided by K here. If we take into consideration derived scaling behavior of the transistor, okay, this electric field is multiplied by alpha factor, alpha times. Okay, so let's say we have a miniaturization version of this MOS devices, and we have a electric field. So what is the new electric field for this miniaturization devices? So it is alpha times the electric field which we have here for this macro devices. Similarly, drain to source current that we commonly also call drain current. So it is multiplied by alpha square times divided by K. Okay, so this is also important thing. Similarly, the capacitance. So the new capacitance will be, it will be 1 divided by K. So it is uh, multiplied by 1 by K. So new capacitance will be reduced by K factor. Now, this is all about the primary scaling factors and the derived scaling behavior of the transistor. Now, if it go to derived scaling behavior of the circuits, that means what is the delay, power or power delay product or circuit density. Then in these cases, the delay, which is nothing but which is the ratio of CB divided by I, that is capacitance, voltage, and I the current. CB divided by I, so this delay will be reduced by alpha k times. So 1 divided by alpha k. Whereas the power, that is voltage into current power, it is reduced by alpha q divided by k square times. So if you can see here, this is very important thing. That means in this smaller dimension devices, we can able to make a we can able to work this the smaller devices in a very small power. So with the smaller power, we can able to function the device. That is very important. Similarly, the power delay product, so that is also multiplied by alpha square divided by k times. And another thing is that which is also very circuit density. That means the number of transistor per unit area is increased by k square times. So this is very important. So two important parameters which we can understand from here. The power is greatly reduced. So that is alpha q divided by k square times. That means with this small power, we can able to work the transistor out of it. And the circuit density, that is the number of transistor per unit area, is increases by k square times. Okay. So this is all about the CMOS scaling that you should know. Okay. So and you should know the what actually the what are the terms and conditions for electric field scaling. Uh, what is the terms and condition for constant voltage scaling, and what is the terms and condition for general scaling. So you should understand and you should know the difference between constant electric field scaling, constant voltage scaling, constant general scaling. Okay. Now, if you can ask me in the normal CMOS industry, what type of scaling is generally used? So basically, the generalized scaling is mostly used in the case. Okay. So, so this is the most adaptable scaling methodology as far as present CMOS technology is concerned. Okay. So now there are some non-scaling factor. That means if you can scale the devices, that means if you can able to miniaturize the devices, there are some parameter that is not affected. Like let's say the band gap of silicon. As you know, the band gap of silicon is 1.1 electron that I'm telling at room temperature. So that is not changed. Okay, the band gap of the silicon will be remain same. Thermal voltage, that is kT divided by Q, where K is nothing but the Boltzmann constant, T the absolute temperature, and Q is the electronic charge. So this thermal voltage also not going to affect. Okay, so these are all some non-scaling factors. So these won't change. That means if you want to miniaturize the devices, these are some of the parameters won't going to change. Similarly, mobility degradation, increasing doping and electric field, velocity saturation, parasitic source to drain resistance, process tolerance. So these are all non-scaling factors. So remember this one, when you want to scale the devices, there are some parameters are there that we call it non-scaling factor. So this scaling factors won't affect this parameter. Like band gap of silicon won't change, thermal voltage will not going to change, velocity saturation, process tolerance. So these are some of the parameters you're not going to change. Okay. So these are some of the non-scaling factors you should know. Okay. So I hope this is clear to everyone. So in this session, we have studied about what is the CMOS technology scaling and why scaling is important, and what is actually the new device structure that is essential for the scaling to be takes place, and the approaches of nano fabrications. So the a glimpse of photolithography process, so for a top-down method, and or if you want to make a device with a bottom-up approach, so what is the consideration is there. And this paper, this research paper, if you find free time, just have a look, because this will give some idea about the scaling behavior. Okay, so I suggest everyone, whenever you find free time, you please go through this research article. And we discussed about some of the scaling principle. That is, first we studied about constant electric field scaling, then we studied about constant voltage scaling, and we studied about generalized scaling. Okay? And what are the difference between these three scalings that we have discussed? Okay. And at last we discussed about what are the non-scaling factors are there. Okay, so these are actually some of the things you should understand. Okay, so I hope this CMOS scaling technology all of you can get to know. So, so this is all about the CMOS technology process. Okay. Okay, so this is for today's class. So we will meet at 4:50 time today in the evening. Okay. So thank you everyone.
Attendance, sir?
That will be recorded.
Okay, sir.
Yeah. So we'll meet those who have lab classes. So I will once again share the Google that Microsoft link. So please join everyone. And those who have theory classes, please join at 4:55 p.m. today. Okay.